Okay, so this is a discussion session on analog electronic circuits internal assessment number 2, that is IA2. So we have a first numerical, that is, I'll just put it highlight on the screen, that we have to simulate a MOSFET differential amplifier. Okay, in a MOSFET differential amplifier, the value of RD and RS will be the last two digits of your roll number times kilo ohms. So, for example, your roll number is 100020, then RD1, RD2 will be 20 kilo ohms, and RS also will be 20 kilo ohms. Okay, so if your last digits, two digits are from 1 to 10, so kindly add 10 to your last digits. So 1 will become 11 and 10 will become 20. All right, so RD1, RD2 and RS will be 11 kilo ohms. So all three have to be same. Okay, so this numerical will be unique for everyone will be doing it separately. Here we have the threshold voltage same 1 volt. Then the device gain, that is kn1 and kn2 is same, and VDD and VSS is plus 5 and minus 5. V in, well, you can take it around 40 millivolt per peak to peak. Okay, and there is some more instructions, but before going there, let me build this circuit in front of you quickly. So this is my LT Spice screen. So you have to select the new schematic, then you go to components, and from those components you select NMOS. So you have to select NMOS 4. Okay, remember to select NMOS 4. So we know what is a differential amplifier, right? So we have one MOSFET over here and another MOSFET over here. Now remember that if you just rotate it, it won't give you the mirror image of it. So we have to keep this gate sides on the right hand side. So how to do it is, you select this. Okay, you select the MOSFET. So I'll copy the MOSFET over here. Okay, now I want to mirror image it. So what I will do is I'll select this, and here I'll press mirror. So the moment I press mirror, the gate terminal has appeared on the right hand side. Okay, understood about this? Okay, any doubt here? So that's the first step. You have to select the MOSFETs. All right. Now, as we know, we have done the experiment number 10 as a MOSFET differential amplifier. So most of the things remains the same. So first of all, this is my drain terminal, gate terminal and source terminal. Okay. So we have two drain resistors. So this is my RD1, RD2. So I'll connect them together. Okay. And then down I have RS. So here I will connect RS. All right. Now I'll join them together. And upper side I'll connect the supply voltage. Okay, this is done. So rename it as RD1. Okay, this will be RD2. And the value we can take it anything. Right now I am not taking this specific values. I can take anything over here. Let me take it as 30k. Okay, this is also 30k. And this is RS. I need to connect it to negative supply. All right. So this is my this is how my differential amplifier will look like. Now I require plus VDD and plus 5 and minus 5. So how to connect this? So what you do is go to components, select voltage, and place one voltage over here, place the another voltage over here. All right. Then upper terminal, you just connect them together like this. The middle one will be the ground. So here will come the ground. All right. Now see what I'm doing. You have to label the above terminal as VDD. You can do it like this or manually connect the wire, and label the below terminal as over here, the wire as VSS, like this. So what it means is here and here I'll get plus 5. So if I give here 5 volt, so this is ground with respect to ground, and this is negative terminal is over here, so this will be 5. Again give it 5, don't give minus 5, because this minus 5 will be connected over here. Now over here I will be connecting one wire. So if I label this wire again as VDD, What this means is 5 volt will appear over here also. Okay, just to remove the this concept is very much used. Okay, while making a PCB also you can label it like this, and here also you can label it as VSS. So let me label it as VSS. All right, RS value was let me take it as, let's say, 16. Okay, I'm just taking examples. So have you understood about the power supply connections, everyone? Yes or no? Just reply.
Yes, sir.
Okay, great. Now the next thing is, there is the fourth terminal. There is the fourth terminal of the MOSFET, which is the body terminal. So body terminal has to be connected to the most negative part of the supply, and the most negative part of the supply is VSS. So take a label from here and label it as VSS. All right, don't connect it to ground. Ground is not the lowest part. So you have the maximum potential phi, minus negative is minus phi, and then you have a ground. Okay, so substrate terminal or the body terminal of the NMOS has to be connected to the most negative part of the supply. So here it is VSS. Now we need to apply input. Now input is given as 40 millivolt, just given as 40 millivolt peak to peak. Now since it's a differential amplifier, we have to apply differential inputs. Okay, so how will you apply them? So here I will be again selecting a voltage supply, and I'll connecting over here and the other one over here. Okay, now I'll make the connections. So this is my gate terminal. I have to connect it to ground. Okay, so I'll connect it to ground. Here also I'll do the same. Let me just push it over here. Yeah, and you have to make the circuit very clean. Don't make it crumbled. It should be clearly visible what you have done. All right, so this is my ground. All right, so here let me call this as V in 1. This is not the label, this is just the supply voltage name, that's it. So just let me call it as V in 2. All right, now right click, I have to apply a sinusoidal voltage over here. So I'll go to sine, and here I have to give DC offset as 0. Input is how much? 40 millivolt. Peak to peak I want to give, so I'll give over here input as 20 millivolt, because this is the peak value. 20 millivolt. Frequency you can keep it as 1 kilohertz. Delay time 0, theta 0, phi 0. This is very important why we take this. Okay, so here differential input means it will be of the same magnitude but opposite in phase. So how will you give opposite phase? I'll right click over here, go to advanced, go to sine. Here you start with 0. Amplitude will be again 20 millivolt. Frequency will be same 1 kilohertz. Time delay is 0, theta is 0, but angle will be 180 degree. Are you getting it? So this is what you mean by differential input, same amplitude but different in phase. So these are my differential input. Then I label this terminal as I in. Okay, I in 1. Let me label it as I in 1, and this will be I in 2. Okay, input 2, input 1. So differential input will be V in 1 minus V in 2. Getting it? Okay. And I have to label these terminals also. So I have did a mistake over here of connecting it very close. So what I can do is I can use this terminal called as drag. So I'll click on this. If you have drawn very close, you can drag it like this. See, are you understanding? So I've dragged it up so that my circuit looks clean, neat and clean. Now I have to take a differential output. So here is my one wire. So please tell the students to join via Somaya link. You can join automatically. Don't join via Gmail account. Okay, so here I label it as out 1, and here I label it as out 2. Alright, so my circuit is fairly ready. I've given all the possible things. Now only thing left is I have to give threshold voltage as 1 volt and Kn as 100 micro ampere per volt square. So how do I do that? I right click, go to draft, go to spice directive. Alright, now if I go to spice directive, I have to write over here dot model NMOS bracket VTO. Threshold voltage is written as VTO equal to 1 volt, space Here in LT Spice, instead of writing KN, we write KP, and KP is normally twice the value of whatever given to you. Okay, so the given value is 100 micro. You have to give over here 200 micro. So how do you write micro? So instead of writing micro, you can write e raised to minus 6. Are you getting it? And then close the bracket. Did you understand how we wrote this? Yes or no? Okay. Now you don't give the same name. Let me call this as NMOS1. So this also will be NMOS1 because parameters are same. So what I'll do is I'll write dot model. The first name is the name which we have given, and the second name is the by default name taken by the spice model. So dot model NMOS1, NMOS, VTO threshold voltage is 1 volt here, and KP, KN value whatever it is given, you have to take twice of that. Okay, and why I've given both of them same? Because both of them have similar parameters. So I'll give NMOS1, NMOS1. Up till here it is clear. Please give me the feedback immediately so that I can proceed. Any doubts over here? Because this is what you have to do. So listen carefully. Up till here, any doubts? Hello? Alright, great. So now we are ready to simulate. Now let's read the question again. Make a circuit schematic of MOSFET differential amplifier as per the above information and attach the print screen of the circuit. Okay, so once you have done this, I have made a document, blank document. What are the expectations from question number 1? Okay, so for question number 1, as soon as you made the circuit, okay, so according to me this is correct. Now I'll take a print screen. Now when you take a print screen, take a full print screen which will show you the date and time also. So let me show you to you how the print screen should look like this. Did you see it clearly? And normally keep the background as white so that there is no ambiguity, and also keep the grid on and keep the possibly the background color as white. Now I'll show you how to do that. So go to tools, go to control panel, go to drafting options, and here you keep the pen thickness a little higher, 4. Okay, now you can go to waveforms, not waveforms, drafting options again. Yeah, color scheme. Tools, you can go to control panel, drafting options, color scheme. So when you see the color scheme, selected items may select the background. In your case, it might be somewhere close to 100 or something RGB. Select it as 255 everything. So your background will become white. See like this. Okay. If you want to make the components and wires also black, so you can make it 000. For black, make it 000. Okay, and for blue there is something else, but that is enough. Rest all you can keep it as it is. Okay, so this is how you can select the background and keep the pen thickness as 4. And also in the waveforms, when you go, keep the data trace width as 3 and cursor width as 3 and font point size as 15. Okay, so please do these things before you start with the experiment. Alright, so I've taken the print screen. This is what first thing you need to do. Take the print screen. Alright, next, but you simulate, in your case you simulate the circuit and then you determine. Simulate the circuit and determine the Q point of the circuit. So how you do it? Anyone knows how to determine the Q point? You have done it once, right? So which simulation profile you will take? Transient, AC, DC operating point? Anyone has any idea? You want to see the Q point. Q point of differential amplifier will be IDQ, VDSQ or VGSQ. Do you know? Hello? Yeah. So you have to select DC operating point and click on OK. Alright. So you get all the parameters. So this is my Q point parameters, operating point parameters. Got it? So here we have ID value for M1 and M2. As you can see, ID value for M1 and this ID value of M2, they are exactly the same. Okay, 2.88 into 10 raised to minus 5. You read it like this. That means 28 microamperes. But if you want a better view than this, yeah, now you can see the wordings are not clear. So what you do is close this. You have simulated with .op. Go to view and go to spice error log. This will give you perfect readings. See here. We have M1 and M2. Okay, we can compare it easily. VGS, VDS, VBS, VT, GM value also it will give you. So all these values are important. So all these values are, you can take a print screen of this, or you can save this data over here. Let me copy this. So these are MOSFET parameters which will be useful for your analysis. So I'm directly you can note it down in your testing. See, all these MOSFET parameters you get from your model, okay, which will be used further for analysis. So that is what the question is. You need to simulate the circuit and determine the Q point parameters and attach a print screen of the Q point parameters. So for you all, in attaching the print screen, what you can do is you can simulate this and attach this print screen along with the circuit. So how to do it is, let me shift the circuit this side. Okay, let me simulate again, run. This is done. Then I go to view, go to spice error log, and I paste it over here. Alright, now expand this. So this print screen you take for the Q point parameters. Got it? Understood this point, everyone? And then you can take a print screen of this. Is this understood? It's compulsory to do it like this. Why I have taken it this way? So that if you want to copy any parameter in the table, you can do that easily over here. Is this clear to you? What you have to do in question number 1 is clear, A is clear, B is clear. Any doubts, anyone? Please reply immediately. Okay, great. Now, next is simulate the circuit, determine the differential mode gain, and attach the print screen of the input-output waveform. Okay, so I'll close this. There is fourth point also, D. For point C, select differential input suitably. I've already done that. I've already told you all, take the amplitude same and take the phase difference of 0 and 180 degree. So that point D is already covered. Now for differential, we want V in of time, I mean differential input and differential output. So this configuration is basically DIBO. This is DIBO because you have dual inputs and balanced output. Whenever output 1 is taken with respect to output 2, it is a balanced output. So I think you all have in your questions also about balanced input and balanced output. Let me expand this. This is DIBO DFAM. Alright. So for transient analysis, I'll cut this .op. And now if I go to simulate, I'll go to transient. Transient means the versus time. So I've given frequency as 1k. So 1 upon frequency will be time. So if I want 3 cycles of waveform, I'll give over here 3 millisecond. And I click on OK. So when I click on OK, I'll get a blank screen. So here you right click, add plot plane. On the first side, what you do is, or you can not add the plot plane at the very first place. Add trace. Now you have to plot V in 1 minus V in 2. So you can write it like this, V in 1 minus V in 2, and press OK. Alright. You see to it that you select a dark color. So this is my differential input, V in 1 minus V in 2. Alright. Now what was given to you? That you have to take V in as 40 millivolt peak to peak. Okay. So here it is coming 80 millivolt peak to peak. So is it fine? Yes, it is fine. Because your one input is 40 millivolt, other input will be minus 40 millivolt because of the phase difference. So this is absolutely fine. Okay, so this is my input. Any problem in this? Okay, if you don't want to do this, then simulate, run. Then you know what you do. If you want to do it directly, place the cursor over here and keep holding it and then place it over here. Again, you will get a differential output only, differential inputs only. So earlier technique what I have told you and this technique are one and the same. Clear about this? Now for a balanced output, for a DIBO output, what you need to do is right click, add trace. Similarly, Vout 1 minus Vout 2 you have to do. Vout 1 minus Vout 2 and press on OK. Got it? So you get a perfect out of phase output and input, you can select a different color. Output is greater than my input. Is this clear to you? Absolutely 180 degree phase shift. So this is what you need to expect. This is what is expected from you, that you attach the print screen when you get an output greater than input only for differential gain. Is this okay, everyone? Any doubts in this? You need to determine differential mode gain. So what will be differential mode gain? Can you tell me? Anyone? So I need to measure the peak to peak value of the output waveform. So what you do is right click on this. You'll get one cursor, select at the maximum peak. You'll get a second cursor, select at the minimum peak. So here I'll select it over here. Wait, this I'll go to maximum and this I'll go to minimum. So top peak to peak value. That means 257 millivolt is my differential output. Alright. So how to calculate the differential gain? So what I get is this is 257. This is V out, differential V out. Okay. And what is my V in? V in is how much? Differential input is how much? 80 millivolt. 80 millivolt. And what will be my differential gain? AD. AD will be V out of differential divided by V in of differential. So you can calculate and calculate your answer, and then you include it over here in the numerical itself, and then attach the print screen of this. Okay, so 257 upon 80 roughly someone can calculate and let me know the answer. So this way you can attach this print screen. So whatever the value is, now this print screen, whenever you're measuring, see like this measurement. So which print screen you have to attach at the output where you set this peak to peak value. So along with this, you highlight this part, then you take the print screen like this. Is this fine? Now, is this fine? Do you understood? Now, since you're doing it uniquely, what you can do is you can write over here instead of V in 1, you can write V in 1 underscore your last two digits of your, or you can write your name. Let's say my name is Inderjeet. So V in 1, V in 2, at least one, at least output or input underscore my name. This should be as a proof. Okay. Yeah. So when I plot the input, it will be like this. So automatically the name has come over here. Okay. So this will validate the uniqueness. Okay. So this you can take the maximum value. Okay, I've got it for the input. Input I don't want. Input I know already it's 80 millivolt peak to peak. I'll go to maximum value over here, and then I'll select the one more and go to the minimum value. So around, yeah, Achha, this has gone down. So around 257. See, okay. So peak to peak value. So this print screen you require is what is expected for part C. So you can attach this print screen over here. Everyone clear about it? What to attach? Your name should be there automatically. If you want to include it over here, that is also fine. But this is what is required from your side. Is this clear? Any doubts? Hello? Great. Now, last part is you have to calculate it theoretically. So basically you have to make a table. Let's say that what parameters you are inputting. You have to make the table. Here you write parameters. So here you write Q point parameters first. So Q point parameters are ID. Okay. So here you can write theoretical, and simulated. Okay, you have to create this table. Okay, so here parameters you can write over here Q point as first ID1, ID2, ID1 comma ID2. So you can write the value. You remember you got a simulated value. Oh, I am doing it over here. I should not do it over here. I'll delete it from here and do it over here. Okay, here it is. I have to create the parameters. You remember we got the value of ID. So same ID value you can write it over here. Okay, I have to write it in the simulation case. So add a simulation case. Okay, then I can write it as VGS. VGS is another parameter. VGS1 comma VGS2. So what was the value of VGS? VGS is same for both, 1.54. So you can write over here simulated is 1.54 volt. Then you have required VDS1 and VDS2. Okay, these are all Q point parameters. So VDS is 5.67. This is example I'm giving. This is not the actual numerical which I have given. And then differential gain AD. What was the differential gain AD? The value was around 257, right? Divided by what? 257 divided by 80. So that is around 3.212. So the gain is minus 3.2125. So here it is minus. Why it is minus? Because input and output, differential input and the differential output are out of phase with each other. So if you fill these values, you know how to calculate it theoretically, right? So use the formulas and calculate it theoretically. If your theoretical answer and simulated answer matches, then full marks for this numerical. Okay, so all the marks you will get. First four are just simulations, and last one is you require some theoretical calculations also. And whatever theoretical calculations you are including, you have to attach, you have to write it on a piece of paper, write the name and put a signature on the piece of paper, then attach it over here, then attach that image of that paper showing that you have done the theoretical calculations. If you don't include that paper, you won't get marks for this question. Is this fine? Everyone understood about numerical number 1? Quickly tell yes or no. Any doubts in? Yeah, any doubts in this? Anyone? So I kept the forum open. If you have doubts, you can ask. You have to do it yourself. There is no other way. Now, the question is, even roll numbers can easily do whatever I've told you. But what about the DIUO configuration? So listen to what you need to do. Listen very carefully. You won't get this waveforms then. So I am talking about DIUO. So what is DIUO full form? Anyone knows? Dual input. Exactly. So here you remove one of the output. Okay, and you try to plot. So input is getting plotted very fine, but output is with respect to ground. So if I plot the output, it will come with respect to ground, but you will get the output like this. Yes or no? So what is the problem over here? The problem is, earlier when we were taking V out 1 versus V out 2, this terminal, drain terminal, this is a drain 1 terminal, this is drain 2 terminal. This contains DC and AC together. Are you understanding? What I'm saying is this. How I explain is this. So this is basically VD1 voltage, and VD1 voltage contains both AC and DC quantities. Okay. Similarly, your drain terminal 2 contains AC plus DC quantities. So when I calculate differential gain VD, what are we doing? We are calculating VD1 minus VD2. Okay, so your DC is getting calculated, and difference in AC comes. So you get only AC output. Yes or no? But this is true for DIBO. But what happens when I take only one of the outputs, VD1? I'll get AC plus DC output. Are you getting what I'm trying to say? Yes. So here if I do DIUO, I'll get AC and DC output. Okay, here I have to remove the minus sign. Yeah. So this is the DC shift. So I have to remove the DC shift. So how do I do that? Anyone? So here, if I have simulated before, so what I'll do is I'll note down one more parameter over here. Okay. Those who want to do this, you have to be very careful. Name it as drain 2 terminal. So I need to calculate VD2. So again, I'll simulate the operating point analysis. Okay. See VD2. So this is only for DIUO people. Okay. So you note down the value of VD2, go to draft, go to comments and note it down. Done. Up till here clear. Now again go to the dot tran, simulate it again and give over here 3 milliseconds. So you got the output waveform, right? Now what you need to do is plot the input. So I'm plotting directly the input, differential input. So this color I'll keep it dark. Okay. Now if I plot the output, I'll plot the output over here. Now it's coming like this, right? This is not correct. I mean, this is not the way we expected. So what you need to do is, this is the DC value of at the point VD2. So you need to subtract this with that value. So you will write minus whatever the value is as it is, 4.1343. And you just click on OK, you will get this waveform magically. Understood about this? How what we have done? We have subtracted the DC component and we got back the original waveform. Is this understood? This is the DIBO output, or DIUO output, sorry. And this is what is expected from you all. So you can take the print screen of this for when you get the output, okay? And then also you need to attach the output here like this. This should be clearly visible. Understood how to take DIUO? So this is one sample example of DIUO. Of course, your values are different, so all of you will get different answers. Remember, in theoretical, DIBO, if it is coming, let's say 3.2, DIUO will come half of it. It will come around 1.6. So you can check it out here. I am not checking it right now, but you will get that way. So understood about how to do the simulation for DIUO. Those who have odd roll number will attempt DIUO. Even roll number will attempt DIBO. So if you attempt the wrong configuration, you will get the 0 marks. You will not get proper marks because it is clearly mentioned over here. Your roll number should be odd or even. Select the proper configuration. Any doubt in question number 1? Yeah. And also the value of RD and RS should be strictly as per your roll number. Strictly as per your roll number. You cannot change it any random value. Okay, we will check it. If we found that there is any discrepancy, then we will discard that question. Meaning, if your roll number ending is 97 and you have taken 27, that is wrong. So you will get a 0 marks for that numerical. Any questions in numerical number 1? Clear about everything? Yeah, you want to ask anything? Yes or no? Hello? You all are there? Someone please give a response so that I can proceed. No. I mean, orally tell me because I'm not checking the chat box. Any query over here? You can ask right now, or else I'll proceed. Yeah. Okay. So yeah. I'll tell you. So you remove this dot run, simulate, run DC operating point. Just label this as D2. Okay. So here we get it. See, VD2. Understood? And this will be helpful. You have to subtract with this value. If you take VD2, some people can take V out 2 also. So there you have to measure for VD1. Got it? Okay. So then this discussion is over. Let me go to numerical number 2. So numerical number 2 is very easy, actually easiest of the all. Simulate a single stage BJT amplifier, common emitter amplifier. I'll quickly do this because I think it is required. Let me go over here to tell you all certain things which you have to be careful about. Okay, so this will help you all to do it. Now only request from my side is do it individually, do not take help of anyone. Okay, because that's the point of keeping this session, that you should be confident enough to attempt a numerical on your own. Okay, don't disturb anyone, do it on your own. It's very easy. I've done it in front of you. Okay, so here and strictly follow the instructions. Now in the sample numerical I have taken RD1 and RS value different. You have to take it same. So read the question carefully. If you take a wrong value, you will get a 0 marks. Again I'm telling, for both the classes A and B division. Okay. So here we have a single stage BJT amplifier. The first thing you select is NPN transistor and click on OK. That's the first thing you select. Okay. Now here R1, R2, R3. So it's a voltage divider biasing. Let me quickly simulate and show it to you. So this is R1, this is R2, this is your RC, and this is your RE. Okay. Now I'll join them quickly together. Simulation is very easy job, but still some people struggle because they don't follow the basic steps. So I'll join them quickly with the wire. Alright. Then I have R1, R2 values are given. Now, most important thing, if I have capacitor, let me show you what student may do mistake. So they rotate it, they do everything correctly. What they do is they directly connect this over here. ऐसे connect करते हो. You know what is the mistake over here? The mistake is these points are not connected. Let me show it to you. So if you don't have a dot, only this base terminal and collector voltage, collector capacitor connection is done. But R1 and R2 are not connected to this. So what you need to do is systematically do it. When you connect the wire, first connect it over here and then connect it over here. This will make the connection. Got it? Most common mistake which student do. Got it? Yeah. Then the next coupling capacitor will be here. And do not, this is a normal C amplifier which you have done many times. So it should come naturally to you. Where are the capacitors connected? So here are the three capacitors. Okay, I will not take these values. I'll take some different value only. Now I have to connect the power supply. VCC is 12 volt. So I'll go over here voltage. Directly I'll connect the power supply over here. Remember to connect the ground also. So whenever two or more wires meet, they connected with this square black color square box. Here it will be 12 and I have to connect the ground also. Alright, all these are common steps. The main step I wanted to highlight was this. Now I'll connect the ground over here also. Sometimes people don't connect the ground over here. It's important to connect the ground over here. Okay. Here I'll join with this. Now, if the value of the capacitor is around less than 1 microfarad, then you select as it is. So let's say this is 1 microfarad. So don't do anything. This is 1 microfarad, let's say. 1 microfarad as it is. Very simple. Okay. Now at the input, now here the question is, make a circuit schematic of BJT-CE amplifier as per the above information and give suitable input. Now what do you mean by suitable input? Very small amplitude and the frequency will be reasonable around 10. I'll give you an example how to take a print screen of this. Okay, this ready? R1, R2 and give the same name. Just call it as RD only. Don't just give it any name over there. Give it as RD only. Okay, this you can give it as RS only. This is CS. This is C1, CC2, or you can give CC1, CC2. That is also fine. Okay. Here I have written. Oh, this is your RE. This is common emitter configuration, right? So this is RE. This is CE. Oh. Got it? Now input what you will apply. Input voltage source you connect over there, and I'll connect it with the ground like this. Right click over here, go to advanced and go to sign. So here you can apply 0. Give a small amplitude 10 millivolts peak. So that will be 20 millivolts peak to peak. Frequency give it around 10 kilohertz. So 10 kilohertz is a reasonably well. Let me enter the values. I'll not take the same values. Rather I'll take a little a lower value than that. Let's say 75k. Okay. Next value is you have to take it as per data given to you. This value is let's say 1.5k and this is 420. I'm taking randomly, but you have to take it as per the given values. Now at the output there is RL also connected. So where you connect the RL? Over here. Okay, this is my RL and here I'll connect my output and this will go to the ground. Understood the connections? This is RL. Okay, this is E2 and this is my V out. So I'll label the terminal as out here. Okay, and this is my V in. I label the terminal as in like this. Clear to you? Or I can label the terminal as V in underscore your name. So I'm entering my name over there and out underscore. Okay, up till here clear to you? Any doubt? Now you have to select the BJT 2N2222. So right click on the BJT, select on pick a new transistor and select 2N22. So but very important to note down its parameters. Its early voltage is 100 and its beta is 200. So this information will be required for solving the numerical theoretical data. VAF is the early voltage and BF is the beta. Okay, right? Select that. So this is my 2N22 transistor. So first thing is make the circuit schematic as per the given information and give a suitable input. So that is what I have done. Now I'll take a print screen of this. Okay, RL value has to be put, that is around, let's say take it as 10k or 1k. Let me see. One more thing I forgot. This has to be electrolytic. So right click on it, select a capacitor, scroll down, search for AL electrolytic, select any value. Okay, and then enter the change, put it as around, let's say 100. I want 100. Got it? How to select electrolytic capacitor? All right. Now I'll take the print screen of this, full print screen including date and time, and then I'll enter the print screen in my wherever document I'm placing, question number 2. That is the print screen. So this is clear to you? Oh, this was there. So I pasted below this, question number 2. Yeah. Understood about this? Now next is measure the Q point parameters of BJT. Okay. Don't worry you have applied AC input or something. Just click simulate, run, DC operating point, OK. If we get this, close this. We don't require this. Actually, if you go to view and spice error log, you will get all the parameters of BJT. So this you have to take it. So for this, you put the schematic in the left hand side, simulate again, close this, go to view, spice error log. All these parameters you got already. So you got a value of IB, IC, VB, VBC. See, VBC is negative. That means base collector junction is reverse bias. VCE value, beta DC. Have you heard about beta AC and beta AC? So beta of this transistor is 200 given in the model, but we are getting around 208. Then GM, small GM. You remember small GM for required AC calculations? Then RPI value. Then RO, small RO value is also given to you. So all these parameters you can note it down and also take a print screen of this. Okay. Sorry for this. Yeah, print screen of this. This is the Q point parameters and then you can attach it in your document. And also locally save these values in your, this thing. I'll show you how. So you select these parameters, and you can compare it with the parameters which you theoretically obtained, and I'll enter it over here also if you require any theoretical value. Got it? Understood how to get this? Alright. Simulate the circuit, perform transient response, perform V in and V out, and determine voltage gain at 10 kilohertz. So for this you need to cancel the operating point analysis, simulate, run, operating transient response. Here I've given 10 kilohertz. So here timing will be 0.1 millisecond. So here I'll give 0.3 millisecond. So I'll get 3 graphs. Okay, the last one I will. So here on the blank screen, right click, add trace, V in. So this is my V in, 20 millivolt peak to peak. Then I'll keep a add plane plot, because if I plot it on the same thing, let me show it to you. It will be like a straight line. See, and you will say the output is not coming. Now output is coming. It's very small compared to the output. Input is very, very small. So what I will do is right click, add plane plot, and I separate it out. Now you can individually measure, right? Input is around, how will you measure peak to peak? You already know. This maximum peak, keep it over here. Take one more cursor, left click, and keep it over here. So it's around how much? 1.45 volt. Don't say the minus sign. 1.45 volt divided by 20 millivolt. That is my gain. Okay. And this print screen, you can take it and attach it in your documents wherever you are saving the data. Okay. Remember, date and time should come. Your name should come. Is that clear to you? Without this, we won't be accepting the results. Is this understood by you? Yeah, everyone? Yes or no? Reply fast, please.
Yes, sir.
Okay. Now last step, compare theoretical and the Q point values and the voltage gain in B and C. So same thing as we have done earlier. Let me show it to you. We have prepared a table, right? So same table you can copy it down, but parameters will be different. Put this table over here and you will have more parameters. You will have IC only, IC, then you will have more parameters will come. Here VBE will come, then VCE will come. Okay, these are Q point parameters and voltage gain will come. Normally these three, if you include, that will be enough. And this we already got from the simulated value. See, IB value is 1 point, this IC is 3.3, VB is 0.686, then GM is this much. So you can cross check these values with your simulated, with your theoretical values. If you're getting any deviation from it, that means you're going wrong in your numerical. RPI is also given. RX, don't consider RX, you won't understand right now. Don't consider RX. RO, this is small RO. RPI, GM, beta. VC, VBC, VB, IC, IB. So all these are Q point parameters. And at the end we require this table. Not with these values, but the values what you have got. Got it? So this is what is expected from numerical number 2, question number D. Understood this or no? Any doubts? Any queries before I move on? Yes, no, what?
No, sir.
Okay, great. For numerical number 3, well, this is numerical. This numerical was already shared with division number A. Division number B, your class teacher will share it with you all. Module number 3, handouts. So if it is already said, it's a similar numerical, but with different parameters. So it will be a practice for you. Here you have to simulate the circuit. Everything is given to you as per these values over here. And VTN, VTN2, zero point 0.8, KN1, KN2 is 1 milliampere per volt square. CGS and CGD. Now what is CGS and CGD? This is my drain terminal. This is my uh, you know gate terminal. So it's the capacitor externally connected between gate and drain terminal. CGS is the capacitor externally connected between gate terminal and source terminal. Alright. So let me just show it to you. I will not draw the circuitry. Let me just show it to you. This is how your circuit will look like. Okay, no need to do this. This basically calculate the frequency response. Most of the parameters are same, but some are different. Also the same thing. Here the body terminal of the MOSFET has to be connected to the most negative part. This terminal will go to VSS. The supply voltage will go to ground, and this capacitor will go to ground. That you have to take care. Okay. And what is the special things which you have to take care is you have to apply a suitable input. So here you cannot apply AC. This is not allowed. So I'll help you out in this. What you need to allow. Here you select the voltage, apply it over here. If you want to change the frequency, right click on this AC. Select AC amplitude as 20 millivolt. Okay, this will make the AC amplitude as 20 millivolt. That is fine. Now this CGD and CGS you have to connect it like this externally. Alright, rest everything is similar to what we have done before, but only these differences are there. KN1 and KN2 is 1 milliampere per volt. So here in the dot model you will write it as KP, and that will be 2 millivolt. So 2E minus 3. VTO will be 0.8, and lambda, well, if you don't give, it will be 0. By default it will be 0. And supply voltage is plus minus 5, like this. Okay. So this circuit I'm not making, I've already made it and kept it ready. So now I'll tell you how to simulate this. Let me close this thing. Alright. Uh, oh, what I did was I closed the earlier turn. Let me see for today IA2 high and low frequency response. Yeah, this circuit it was. Same one. Okay, here it is 20 millivolt. Yeah, that is fine. This is the same circuit. Now let me simulate this. So after making the circuit, what are the expectations is? Create a circuit schematic of MOSFET CS amplifier in LT-SPICE as per the given information, and give suitable AC input. So AC input you have to give this. Why we give this? Because we want to vary the frequency, And so for varying the frequency, you have to give AC amplitude as 20 millivolt. You cannot give a frequency value. So if any student selects sine, that will be wrong. If you give sine, that will be at one frequency, but we want a variable frequency. So you select none and then select 20 millivolt and then OK. All right. And you take the print screen of this. This is not required actually. This one is not required now. And run. Okay. Before running, you can take a print screen. I know it's working, so I will take the print screen of this and attach it in the document where I'm storing all the data. So here I write question number 3. This is my print screen. Okay. Of course, you have to write your name, v underscore your name, v out underscore your name. Okay. And you can also write your name and roll number in the comment section in big letters. All right. So I'll simulate this. Now here I'll add trace. I'll plot V out. If I just plot V out, that is wrong because this is the gain. So I'll plot V out divided by V in. This is my output, proper output. Okay. So I'll right click over here, red color. This is the phase plot. So we don't want the phase plot, remove it. So don't phase plot. Okay. Now you already know how to calculate the bandwidth of a system. Maximum dB is 11.39. So you have to go 3 dB down. So that will be 8.39. So go 8.39 somewhere around over here. Yeah, 8.41, that is close to 8.39. And here also. Here also you have to go close enough. 8.39. Yeah, 8.4 it is. Yeah, it is 8.4. So this lower value is my lower cutoff frequency FL. This is my FH and this is my bandwidth. Don't consider negative sign. This is my bandwidth, 6.3 megahertz. Got it? So this print screen you have to take when you get for your values and then attach it in the document where you are saving it. Attach the print screen. Got it? Understood? Everyone? So simulate the circuit, perform frequency response and determine the midband gain. What was the midband gain? You already FL, FH and bandwidth I told you all. These are FL, FH and bandwidth. What was the midband gain? This was the midband gain, 11.39. So this is my midband gain. Okay. And this you have to go 3 dB down and then take it. So your question number B is completed. Then you have to create a theoretical table for midband gain and FH value. Okay. So again you can copy the table. Okay, and that was saved in another document. Again copy the table. Let me do it over here. Yeah, this one. Now the third case, you have to compare what all things. You have to compare um, what was asked to you. Midband gain, that is AV, and FH. So only two things you have to compare. So AV, these things I'll delete. So only two things I want, AV and FH. Okay, simulated we already got it, 6.3 something we got, and theoretically. So this is what is expected for question number 3, and this has 4 marks. Point number C has 4 marks, point number B has 4 marks. Okay, so this is the way you get the entire 4 marks, and these calculations are little lengthy. Midband gain and FH, you have to calculate first the DC parameters, then the AC parameters, and then the midband gain, and finally FH value. Okay, so it's a numerical. This point C is a little lengthy, but it's sample example is already said with you all, so you all can refer that and quickly calculate these values. Only some parameters are different. Okay, so that's all about your IA number 2. If you all follow the steps and if you all do it perfectly on your own without making any mistake, you will surely get your all your answers correct, and you can verify them. If the theoretical values and simulated values are coming correct, that means you're going in the right direction. So it's a very scoring. IA2 is very scoring. Only thing is you have to commit yourself and prepare well and do it systematically as I have shown in the video. Okay. So all of you, best wishes for your AEC IA number 2. If you have questions, I'll wait for 1 minute.